Right. Let's continue. We left off, we introduced the block diagram of an SRLH. Two inputs, S and R, two outputs, Q and Q bar. What is a latch? Is the memory element of a sequential circuit. It stores information. Information is stored here. Right. We came up, I gave you the truth table. Right here, we have the truth table. And I said I'm going to explain how we came up with the truth table so that you can do the same for the other latches, for the other flip-flops that we'll be talking of, that we will discuss during the course of the semester. All right, operation. Let's begin with the NOR gate.
Sir.
Yes.
That Q, I found it a Q plus.
Yes. Q plus, next stage. Thank you very much. Q plus, that's the next stage. Right. The operation, we begin with how does the NOR gate operates. This is our NOR gate with inputs A and B and outputs Y. We give our NOR truth table. So we have A and B, 0, 1. Nope. It's not okay. Let's put it right here. A, B, and Y. 0, 1, 0, 1. Participate. What are the outputs for that NOR gate? Output number 1. 1,
0,
0, 0, 0. How the SRLH begins with understanding how the NOR gate functions. That is the operation of a NOR gate. But look what is happening here. If I have one of the inputs, if I have one of the inputs equal to 1, what is the output? It is 0, whatever the other input is. If B is equals to 0, if B is equals to 1, the output remains 0. So if I put a 1 here, whatever is right here, the output will be 0. That is how the truth table is. That is what the truth table is showing us. The other part, if one of the inputs is 0, the output is the complement of the other input. What do I mean? In this case, if we have a 0 here, whatever is here will be complemented as the output. So if I have a 0 here and I have a 1 here, the 1 will be complemented and I have a 0 on the output. It's being showed by the truth table. If one input is 0, the other input B is complemented and we get the output. Those are the characteristics of the NOR gate. Those are the characteristics which will be used by the SRLH to store memory. As you can see, to store information. As you can see, storing of the information is on the memory state. This is where information is stored, this state here. The input doesn't change. Right. Case number 1 for our SRLH. Case number 1. We are now going to take the NOR truth table here and we expand it so that it fits to the SR truth table, SRLH truth table. How do we expand it? We have case number 1. We have 2 gates here, 1 and 2 in red. If R is equals to 1, S is equals to 0. What is this state called? I gave you the name of this state. If R is equals to 1, S is equals to 0. State name.
Reset.
This is the reset. Reset. When S is equals to 0, it's reset. These are the simple things you need to understand. When S is equals to 0, it's reset state. This is case number 1. What it means when S is equals to 0, we have a 0 on here. We have a 1 here. Now, using the operation of the NOR gate, that means using this truth table. What is the output here? What is the output here? Using the same logic I used for this truth table here. The output is, I can't anything. Who is that? Murundi is where up. Murugo on screen.
Yes.
So it means I can't anything. Problem with your network. All right. I was saying, case number 1. Case number 1. We have the reset state. We want to study the reset state. How does it come to happen? Using the knowledge of the NOR gate and the truth table. If S is equals to 0 here, one input of the gate number 1 is 0. What is the output? If one input
will be 1.
Why 1? It's not 1. The output will be the complement of the other input.
Q.
It will be, nope, it's not Q. It will be the complement of this. If one input is 0, the other will be the complement of this. Right. We leave it like that. We go for the case when R is equals to 1. When R is equals to 1, what is the output? Participate. What is the output?
0.
0. Whatever the case, if we have one of the inputs of the NOR gate, the output will be 0. So for this case, when R is equals to 1, gate 2 is output 0. This means Q is equals to 0. What of the other one? Chat. I can't hear anything. Okay. The other one. Now we have a 0 here. It means we have a 0 here. What will be the output? 0, 0. Gate number 1 output becomes 1. Gate 1. Q bar is equals to 1. Case number 1, reset, done. Case number 2, set. You do the same thing. That's the logic behind this SRLH. Case number 2, we now have a 0 here. We now have a 1. This is the set state. Case number 2, S is equals to 1, R is equals to 0. This is the set state. It means here we change. We now have input S is equals to 1, R is equals to 0. When S is equals to 1, the output here becomes 0, whatever the other is. So it means my Q bar now is 0. Automatically my Q now is 1. That is how the SR flip-flop, SR latch functions using the knowledge of the NOR gates. We have a case where S is equals to 0, R is equals to 0. Case number 3. As you can see, the outputs we are getting here, they correspond to the outputs of the SR here. They correspond to the outputs here. So let's have case number 3, where S is equals to 0, R is equals to 0. Right. So if we have a 0 here, if we have a 0 here, the output here will be the complement of this. Right? The output Q will be the complement of Q bar from the truth table. If one of the inputs is 0, it means the output will be the complement of the other input. So here, my input here, let's say my input here is Q bar. I have a 0 here and a Q bar. What it means, the output here will be Q. Q is the complement of Q bar. If I have a Q here, it means I'll have a Q here. If I have a 0 and a Q, the complement will be a Q bar. So you see, Q remains Q, Q bar remains Q bar. Then we have the hold or the memory state. I really feel it's important to understand how we are coming up with these memory, reset, and set states. This is how we come up with these states.
Sir.
Yes?
Sir.
Yes.
Loko kumbirwa kuti S3 mungoidzokorotsa.
All right. Number 3. Let's repeat. No problems at all. Case number 3. S is equals to 0. R is equals to 0. So we have a 0 here. We have a 0 here. From the truth table, we know that if one of the inputs is 0, the output will be the complement of the other input. Because here we have a 0, the complement output 1. We have a 1, the complement output 0. If the input is 0, then this will determine these two here, will determine the output. The complement of this will be the output. All right. Now, what is the input here? Let me draw this. What is the input here? The input here, let's say is Q bar. It is Q bar actually, not let's say, it's Q bar. The input here, we have Q. Since here we have a 0, the output here will be the complement of Q. What is the complement of Q? Is Q bar. So if we have this, it means the information is being stored. Q bar, that's memory. The output was Q bar, and it remained Q bar. For this case, this part, we have Q bar here. Since we have a 0 here, the output will be the complement of this. What is the complement of Q bar? The complement of Q bar is Q. We have a memory state. Q is being stored. And this, everything we just did here, it sums up how we came up with this truth table here. This one is the most important to understand. Background information is important for learning part, process. But where we want to get is here. Set, reset, so this is the memory. reset, 0, set, output 1. This is illegal. That is the truth table of the SR latch. Now we have what we call the state transition table.
What are purchases for X?
State purchases for X is illegal. I can say, okay, let's not put in X. Let's put this. It doesn't exist. Much better. Or let's put this. It's not necessarily an X, which means anything. Let's put a question mark. It's illegal. That state doesn't exist. This state right here, it does not exist. In fact, I missed it. Let us explain why it doesn't exist. We have a NOR, right? Let's explain why it doesn't exist. I'll explain why it doesn't exist. For the other state, we explained why they exist, why it's memory, why it's set, and why it's reset. Let's explain this one. So we have S, we have R, we have Q bar, we have Q. What happens when S is equals to 1 and R is equals to 1? This is the illegal state, right? Get 1, get 2. What is the output of get 1? Truth table of NOR gate. Let's put the truth table of NOR gate here. A, B, F. 0, 1, 0, 1, 0, 0, 1, 1. Here we get the 1, 0, 0, 0. What is the output gate number 1? Using that truth table. I'm listening.
It's a 0.
It is 0 because if we have a 1 here, if we have a 1 as one of the inputs, the output will always be 0. So we have a 0 here. Here, we have a 0 here. This state doesn't exist because here we have a Q, here we should have a Q complement. What is the complement of 0? It is not 0. So for any state in the SR latch, which has the inputs 1, 1.
Complement of 0 and 1.
Yes, the complement of 0 is 1. That's why we have an X there. Because here, as you can see, the output of these gates, they are both zeros. But we are supposed to get a 0 here and a 1 here. Or a 0 here and a 1 here. Because they are the complement of each other. If we don't get that, we get a 0 and a 0. We call that an illegal state. It does not exist. Voila. From the truth table, we go to the state transition table. State blue. From the truth table, all right, let's draw the truth table. This is for the SRLH. Right, for the truth table, we have SR, then we have the next state. We have 0, 1, 0, 1, 0, 0, 1, 1. So here we have Q, hold, reset, set, illegal. So this is memory, reset, set, illegal state. All right. We have the state transition table. Or let's say the characteristics table. Characteristics. Some sources they say state transition. Well, let me say this is the characteristics. Table. You need to know this as well. Here we have the truth table. Now we have the characteristics table. What is the characteristics table? The characteristics table allows you allows you to find the next state of the flip-flop. Allows finding next state of flip-flop or a latch. It allows finding the next state of the flip-flop or the latch. How does it do it? It has 3 inputs. For this one, particularly the SR latch, we have my input Q, then I have my other inputs S and R. So we have 0, 1, watch 0, 1, 0, 1, 0, 1, 0, 1. For 3 inputs, I will have 8 possible outputs: 0, 0, 1, 1, 0, 0, 1, 1. I have 1, 2, 3, 4. 1, 2, 3, 4. It allows finding the next state. This is my next state. Let's say at the present, my state is 0. My inputs of the SRLH, they are 0, 0. When I have a 0, 0 here, what is the name of this state? Participation. When I have a 0, 0, name of the state is right there on your screen. If my inputs are 0, 0, what is the name of the state?
Memory state.
It is the memory state. What the memory state means, it means my present state is equal to my next state. It doesn't change. So if I have a memory here, I'll have a 0 here. Why? This was my present state here. Then move on to the second row. I now have a 0 and a 1. Name of the state?
Set.
Reset.
Oh, sorry, reset, yeah.
A 0 and a 1, this is the reset state. From the truth table, what does the reset state say? The output, the next state will be a 0, whatever the input was. I'll have a 0 here. The next state, this is the set state. Whatever the input, it will be a 1.
Reset.
The next state, this is illegal.
Illegal.
We don't have anything here. Here, we have a memory. It means what my present input, my present state was, it will be my next state. My present state was 1. Memory is holding 1. I have a 1 here, but I have a reset here. A reset means a 0. A set here means a 1. I have another illegal state. So what you need, what is important? Red. What is important to get? This is how you come up with the characteristic table. Characteristics table. 0, yeah, 1. Yeah. Right. It's important to understand what we have here. The memory state. The state doesn't change. 1 here. This is where all the sequential circuits are. The memory part. So if you want to store a bit 1, if you want to store a bit 1, what do? Your SRLH, we have the inputs 0 and 0. Your SR, we have the inputs 0 and 0. Then your 1 is stored. If you want to store 0, 0 and 0, my 0 will be stored. If I want my output to be 0, I change reset state. If I want my output to be 1, I change set state. From the characteristics table, this is how it shows what is the next state of your sequential circuit. The next state will depend on the inputs S and R. I think we are done with the SRLH. So what you need to know is these two truth tables. So what I did, because when I did these things, I didn't understand what was the memory state. I didn't understand what was the reset state. Why is it called the reset state? Why is it called the reset? Because the output will be 0. Whatever the input, the output will be 0. That means reset. When the output is 1, that means set. When the output state is the same as the input state, the last state, it means we have a memory. Now I didn't understand all that. What I did, I crammed this table. I was very good at that. I crammed this table. I know for 0, 0, I write memory at the end. For 0, 1, I write reset. I crammed the characteristics table as well. Once you have this information, it will be easy. Exam time. When a question comes, you will be using this and this to respond to the questions. Either you understand what this is or you cram it. The problem with cramming, though, it doesn't allow you to think. When you cram, once I mix up a little stuff, some little things there, it means you'll be totally lost. That's where understanding comes there. So if you don't understand, at least cram. That's the easy part. We have the truth table and the characteristics table. 9 minutes. Questions and comments so far. This is for the SR ledge. Questions, comments, I'm listening.
That would digest.
Still digesting. Still digesting. Okay. No questions, no comments. We move on. We move to, do I have the time here? 10 minutes, yes. We move on to discuss the clock. I mentioned there is a need for sequential circuits, synchronous. For synchronous sequential circuits, there is need for a clock. What is that? There is need for a clock. So there is need to understand how the clock functions. Where does it initiate a change? In our SRLH, there is no clock. This was our SRLH. It doesn't mean it's a sequential. It is used in a combination of circuits. Nope, there was no clock here. For the SRLH, Q bar Q. No clock here. It only means this is a synchronous, asynchronous. Asynchronous. Sequential circuit, no clock. So the SRLH is asynchronous. But when we talk of synchronous circuits, though, there is need for the clock, and there is need to understand how the clock works. Right. I already mentioned for the SRLH, the output state changes directly in response to the change in the inputs. For the SRLH, if the inputs change, the output also changes, depending on what the inputs are. That is an asynchronous operation. However, sequential circuits, they employ the notion of a synchronous operation. That means the output will depend on the state changes being made, not by the inputs, but by the clock. The clock decides the timing of the inputs. So the inputs, they no longer change as they want. They change if the clock says the input should change. This is a typical example of representing a clock. logic levels. This is the clock. Minute 6. Yes, I can finish up. So this is the clock. Logic levels. When you talk of logic levels, so here, this is a high. This is a 0. For this clock, we have a period T, time taken by the clock to complete one cycle. So the clock, when it moves from this point and comes back to this point, this is called a cycle. It has a period T. The frequency of the clock is 1/T. I can change. If I want my sequential circuits to be fast, it means I change the frequency. If I increase the frequency, then I have my sequential circuits going from slow, 0, 1, 2, 3, 4, every period. If I increase the frequency, I go to 0, 1, 2, 3, 4. That's it. If I increase the frequency, then the clock moves faster. The changes are faster. There are what we call triggering methods. On this clock, we have what we call triggering methods. From the clock, we have what we call triggering. Triggering is what causes the state to change. How does the state changes? We have different methods to change the state. One, we have edge triggering. Edge triggering, and edge triggering happens here. So when the clock goes from low to high, here, when the clock changes from low to high, this is what we call positive edge triggering. The state can change here, only here. So when we are here, when the clock is on this stage, nothing changes. When the clock is on this stage, nothing changes. Nothing changes. When it comes here, there is another change. That is positive edge triggering. We also have negative edge triggering. Here, when the clock moves from 0 to 1. So from 0 to 1, we have positive triggering edge. Triggering. When it moves from 1 to 0, we have negative edge triggering here. So it means the state changes only when the clock is at this stage. Here, no change, no change, no change. And when it reaches here, there is a change. Negative edge triggering. So for edge triggering, we have negative and positive. This information will be crucial as we move on. Understand what I mean by negative triggering. So the next time, I'll just say, I have a sequential circuit, which is negatively triggered, which is negative edge triggered. You have to understand the changes only happen here. Edge triggering. Right. We also have level triggering. Edge triggering, we also have level triggering. So here we have level, 2 minutes. We have level triggering. Now level triggering appears here. We have low or high. Low or high triggering. So what do I mean by low or high? We no longer have changes here. Read out. So the changes okay at this stage. Red. Nope. Let's put green. The changes, if it is high level triggering, the changes will okay here. They will not okay at this stage or this stage, but they will okay here. If it is low, the changes will okay here. You get the sense when we start giving out examples. The state changes here when the clock is on the low level. Triggering methods, we have edge and level. Edge, negative, positive, level, low, and high. You need to understand also the effect of increasing the frequency of the clock. If I increase the frequency of the clock, it means my clock becomes faster. Blue, 1 minute, frequency is equals to 1/t. So once I add a clock to my sequential circuit, it means I need to understand triggering methods. I need to understand the effect of frequency. Another session soon after,